Today we're going to talk about stress concentrations at a sharp crack. Now, the foundations of fracture mechanics can be originated from the work of Griffith in 1921, where he used the stress field calculations for an elliptical flaw in a plate developed by Inglis in 1913. Now, before we get to that derivation and the foundations of fracture mechanics, let's note the difference between the stress concentration factor approach that we've already learned and the fracture mechanics approach that we're going to learn. All right. So with the stress concentration factor, we are concerned with what is the maximum stress at our concentrator, at our defect or our concentrator in our structure. In order to evaluate that max value, we often calculate the net stress in the vicinity of that stress concentration. So we take the area near the concentrator as our base value against which to evaluate what the max value is, right? Now in fracture mechanics, we do something a little bit different. In fracture mechanics, we're focusing on sharp cracks within a structure. And in the vicinity of those sharp cracks, we're going to learn that stresses are very large. So rather than using the net area stress, instead we use the remote stress. So the stresses that we assume are very far away from our crack, right? So it's important for us to know that there's a difference between these two approaches, the stress concentration factor and fracture mechanics, which we are now learning, right? So with that in hand, let's now consider Inglis' solution to an infinite width plate with an elliptical hole in that plate. So in Inglis' solution, he derived the stress field equations for this specific geometry. He derived where you can calculate every value of stress for this specific type of geometry. Now, if we choose one location, which is the edge of our elliptical hole, and we say, well, what its position is, we can find that the maximum stress at the edge of that elliptical hole is equal to 1 plus 2 times A, which is half of the width of the elliptical hole, divided by B, which is half of the height of the elliptical hole, all of that times our remote stress that's applied at the end remotely, very far away from this elliptical hole. Now let's evaluate this equation for a couple of different conditions. Let's say that we had a circular hole. Say that ellipse was such that the dimension A equals to B. In that case, we have a circular hole, and if A is equal to B, then the maximum stress near a circular hole is equal to 3 times the remote stress. This is perfect. This is the exact solution that we would expect for the stress concentration factor approach, the approach that we previously learned, right? For regular concentrators. But now let's consider another case. Let's consider the case of an infinitely sharp crack. This is the case where the height of our ellipse approaches 0, such that the ratio of A over B approaches infinity. In that case, the maximum stress is 1 plus 2 times infinity times our remote stress. So our maximum stress is equal to infinity times the remote stress. That's impossible, right? That is telling us that for any infinitely sharp crack, any hairline crack in our structure, the maximum stress is equal to infinity. And subsequently, the stress concentration factor, the KT factor, is equal to infinity. So this conclusion tells us that the stress concentration factor approach is not viable for sharp cracks, that it stops working, that it breaks down. And any hairline crack in a structure, any defect or scuff with a very sharp crack in it should lead to instant failure. We're at infinite stress. The part should just fall apart under gravity, right? Clearly, that indicates that mechanics of materials stops working with very sharp cracks in structures. And so we need to develop or derive a new method to deal with cracked bodies. And that method is called linear elastic fracture mechanics.